cloud. Okay. So I'll share my screen just to show the title of the paper. And then we can, but then I want to do some stuff on the board. So the title of this paper is Maximum Entropy Inverse Reinforcement Learning. And I chose it because I thought it would be cool to do a paper on inverse reinforcement learning, because it's like an interesting problem that probably a lot of people haven't heard of before. But so I wanted to break down the title a bit. So I'm going to stop sharing my screen and go towards the whiteboard. Okay. Hopefully you can see the whiteboard. I'll just bring a little bit forward for people. Okay. So the first concept I wanted to talk about is like, what does maximum entropy mean? And they say it in the paper. It's that while still matching the expectation of the distribution. So actually, like for a one-dimensional continuous distribution, a Gaussian is a maximum entropy distribution. And that's because it has the most amount of uncertainty that's possible while still like, so what it means is like the mean is the expectation of your sample, would be the expectation of your samples. And the mean is the expectation of the distribution. And then it has the maximum amount of uncertainty possible within the distribution while still like integrating to one.
I think here the variance is important. The portion is maximizing variance.
Yeah.
It's like,
well, so variance is the uncertainty.
Yes, but say if you take the variance condition away, you get the exponential, which is I think what they did in the paper.
Yeah. Okay. But so and they use this idea of maximum entropy in the paper as a constraint. So they're saying, given the information we have, let's learn the distribution that has the most uncertainty while still matching in the expectation of the distribution with our empirical data. So that's maximum entropy. And then the other idea is reinforcement learning. So reinforcement learning, RL, is learning from experience. And you have like a lot of extra components to a learning problem that has reinforcement learning, which is because you have to, in order to learn from experience, you basically have to define some kind of environment. So the components of the environment are like the state space, which is a set S, and like a really common reinforcement learning environment is called grid world. You see it in a lot of papers. And it's just this, it's like a set of a grid of state place of positions. And you have, usually in grid world, like you have an agent and it starts like here and it tries to get here. So you have your state space S, you have your action space, which is another set, and it defines the set of actions that you can take usually in each state. So like from this state, you could probably go here or here. And then from if you were here, then you could go in these directions. And then you have a reward function. And like in grid world, when you're trying to go from like here to here, usually the reward function could be something like 1 when you get to this state and 0 or elsewhere. And then you and so you're trying to find a policy that takes you to this state here. And the last part of it that you need to make all the math work is a distribution over your first state. So with reinforcement learning, you take multiple steps in when you're interacting with the world. So you could start here, and then in step 0 you're here, and then in step 2 you're here, and 2, and so on. And so in order to make all the math work, you have to define a distribution over initial states. Like one could be just a uniform distribution, so you could start anywhere, but another one could be like you will always start here. The reason why you would do something with reinforcement learning is like the main reason why the reinforcement learning problem was defined is because you have these problems where the search space of solutions is massive. And if you explored all of them, then it would be intractable. Basically, you have like it would take so much time that it wouldn't be useful. And so in reinforcement learning, what you're doing is you're constantly doing this trade-off between exploration and exploitation. So it's like, given the information you've already gathered, what's the best decision you can make? And also maybe you want to gather more information so you can make better decisions. And the signal that you use to choose like to take good actions is your reward function. So that's what tells you what's good and what's bad. And defining a reward function is actually like a really key part of reinforcement learning. If you ever do research in reinforcement learning, you'll find that you get like massively different behaviors based on your based on your reward function. And getting the behavior you want is actually often very difficult because you don't know what's a good reward function. And so, and another interesting aspect of reward functions is that they're the learning signal that you use to train your policies as well, or your value functions. And so, where do I want to go with this? Well, two things is like, there's like really easy reward functions to define. For example, if you have a task you want to accomplish, you can just say, like I did here, 1 when you accomplish the task and 0 elsewhere. And that's clearly defining a reward function that tells you how to accomplish the goal. But the problem is it's what we call a sparse reward function. So say your agent never gets here, they'll never see that reward. And so often people will define what's called like a dense reward function, which is one maybe that says like you take the distance between you and the goal, and you want to maximize the you want to minimize the distance between you and the goal. And then at each time step you'll get a reward function. But one problem with that would be like I'm going to struggle to define this, to draw this correctly. Let's see. What I'm trying to say is like, what if it maybe yeah, it would be like, say there's okay, yeah, say there's a wall like here, so you can't go here, and you have an agent which is trying to minimize this distance. What could end up happening is that they learn to go here through exploration, because this is really close to the goal. And really they have to take a longer path to get to the end. And that's when like a dense reward function, dense reward functions have trouble overcoming what we call like bottlenecks. So you would learn to go here because it's quicker, but then you would never learn to go here. So yeah. And so the reason why I'm saying all of that is because what inverse reinforcement learning is about learning the reward function based on expert behavior, or like somewhat expert behavior. So you have agents who have interacted, like walked around in grid worlds, and you're saying they've performed really well, and I want to define and learn the preferences that they use to act. And so I'm going to try to figure out what the reward function is. So it's trying to figure out what were the preferences of the agent in the experience that you have seen. So that's the two concepts, which are reinforcement learning, and then the need for a cost function in reinforcement learning, or reward function, and then maximum entropy, which is most uncertainty possible. And then I'll share my screen. Here. Cool. So yeah, this is a pretty old paper. I also like this paper because I like the the experiments that they applied it to, or the application of the problem. So they say in their abstract that inverse reinforcement learning, it says this approach reduces to learning the problem of recovering a utility function that makes the induced behavior by a near optimal policy closely mimic the behavior demonstrated. So you're trying to find a utility function that, like we talked about, like has a high probability of recovering the demonstrations that you have available to you. Let's see. They also call it imitation learning, which I've read this paper like a couple years ago, but I forgot that they consider these two things the same, because the imitation learning that I've seen in the literature is usually when you have a set of behaviors and you're just trying to learn a policy that can mimic those behaviors. Whereas this one is trying to figure out a cost function which explains the behavior. So I actually consider it a more difficult problem. Let's see. The key notions. Yeah. Yep. Okay. So the introduction is just introducing the problem. And one of the key ideas, which hopefully I'll be able to explain well later, is that trying to recover the reward function, even when you have it in you've parameterized your reward function, so you know which model you're trying to learn, is an ill-posed problem, because there's multiple solutions that can explain the same set of behaviors. And that's what this paper is trying to address, as like the key thing it's trying to address. Yeah, and then they talk about how they're applying their method to root preferences, but we'll get to that later. Okay, so background. A really important symbol in the math, which just to remember for the future, is zeta, because that defines a trajectory. So it's the set of states and actions that you perform along the way, and you see it throughout the paper. And basically, what they do is they define their state space. By the way, the notation in this paper is a bit dated. So it's a little, if you're used to other reinforcement learning papers, it's a little bit different. But so the state space for them is actually a set of a feature space that they use as their method in their method. So like, maybe I shouldn't have erased that. But anyway, like the state space in grid world would just be the coordinates of the agent. So like 1, 1, 1, 2. But they say they open it up that you could have other things describing the state, like other features describing like in another example in the experiments is that it could be your position, but also like the type of road you're on. So like highway versus local road, like speed limit, that kind of thing. And I actually think that's a really important component of this paper, because kind of the method that it's describing and the types of reward functions it could learn are based on like they weight those other features besides position a lot.
Is it actually important that the actions don't change the features, right? So the action changes the way you are on the map, but it doesn't change like the temperature at the point that you go.
Yeah, that's
that probably is actually important, how the functions actually chosen.
Yeah, I think they state it later, but yeah, I think it is very important. And so like the first really key idea to make the math work of this paper is that you're learning a linear mapping between your state and the action the reward that you receive. So the reward function is defined by so in each state in your trajectory, so S in zeta, you take essentially the dot product of your reward weights times the features in your state, and then you sum it over the trajectory. So your total it's basically your total reward is your total reward is what you could do is you could take all the features of all the states that you've gone through and sum them, and then multiply that by your feature vector, and you would get your reward vector, and you get your actual reward. Yeah. Do you want, should we, does that make sense, or do you want to draw it out, or? Okay, cool. And like, okay, I always like really like clear examples. And so the main thing that we said before is that the problem that you have is that there could be multiple vectors theta, or so like reward weightings that give you the same have the same expectation over the demonstrated behavior, the demonstrated trajectories you've seen. And like a really good one is just putting all zeros in theta. Because if all zeros are in theta, then all trajectories are equally weighted, like likely, and then everyone that you've seen makes sense. Yeah, so like that's what they call the degenerate case, when you just have all zeros in your reward vector. Then they talk about, so that's just something to keep in mind. And then they just talk about another method that's, I guess, closely related.
Last question.
Yeah.
So if you're trying to find a linear mapping, are you essentially trying to solve a linear system of equations? Because it's a multiply, and you have a
The observation is the nonlinear function, I think, of the linear function.
So one thing that so the states are multiplying the elements of the states.
Mhm.
So it's not weighing each different state differently. It's just weighing the components of the state.
And the theta is position independent.
Yeah, it's the same for all state. And so, yeah. What I was going to say is that like a key idea here is you have access to a set of expert demonstrations. So it's the expert demonstrations which give preference to different states. And it's the, as well as, yeah, and then you're trying to figure out what reward vector corresponds to that. Like those preferences that you see by the expert demonstrations.
Which probably is still very limited, like if you think about the text about if there's like a road where it is difficult to turn left just because of the ongoing traffic is particularly strong on that road. Suddenly you have like action potential, right? Because now the action to the left is heavily penalized.
Yeah.
This would be impossible to capture this.
Yeah, maybe do you know why does it have to be a linear function?
So the math works out.
But can't it be a non-linear, or is it because they're trying to demonstrate that it's fine?
Well, they have provable guarantees about the convergence and performance of this method, which only works with a linear function. Yeah. So that's why it's linear.
there has been work after this with no linear function.
Oh yeah, for sure. I'm actually there. I think Chelsea Finn did a paper in like 2016 where she extended this to nonlinear functions, but there's no proofs guaranteeing performance or convergence or anything. Yeah. Classic machine learning.
This is a very common physics problem actually, because it's the only good particle interactions. Solutions. Sometimes you can still calculate it, but it's only rare cases, but not real cases.
So one thing I'll say is, so they talk about another method, which is called structured maximum margin prediction. And basically what they say is the way that they, I'll just read it over here. They demonstrate that this matching is both necessary and sufficient to achieve the same performance as the agent if the agent were acting and solving an MDP with a reward function linear in those features. Oh, that's not where it's going to stay. But basically, they use the probability of a certain trajectory in order to prefer like certain trajectories over others, which this one doesn't do the same thing. Actually, later there's a good example of this in the experiments. Anyway, so we'll talk about maximum entropy IRL now. In stochastic. Oh yeah, so this is the idea of maximum entropy. It says this principle leads us to the distribution over behaviors constrained to match feature expectations while being no more committed to any particular path than this constraint requires. So one thing I was a little bit unsure about this is if it means like, so your feature expectation, what that means is like for each path you sum up your features and you get like a feature count, which is this number here. So you have for each state, you have a set of features, you sum over the trajectory, you get a feature count. I was wondering if what they said when they said match expectation is that you, like if you averaged over all the trajectories you have access to, would you get is that the expectation that they're trying to match?
So that is actually quite common problem that. But what this actually says is, say, someone will tell you feature 1 has the expectation value 5.
Yeah.
Then, if you don't know anything else, you would assign e to the minus 5 times some factor to that feature distribution. If you know nothing else, so it's a sort of external constraint. Does it make sense? Yeah, I'm not sure. But one of the things I'm wondering is path length. Does path length, because the longer the path, with the more features it kind of.
That's true.
And that could potentially get speed thing up.
Yeah, but the feature expectation is maintained by the method. Because you just.
The expectation per second travel, right?
Well, so each feature has an expected value towards the total distribution of each feature. The expected value is maintained.
Yeah,
Because you just multiply by a constant, right? So
Yeah.
I think that's probably.
In the
The refactor does it, right?
No, for sure, the expectation. Well, I mean, yeah, the expectation is maintained safe for the theta part. The theta is the parameter that you're trying to find. But otherwise, just summing all the features.
So in the example, they use a negative rewards, so a cost function. So that would definitely prefer shorter paths over longer paths.
Yeah.
I don't know how.
But that almost is general, right? Independent of the feature.
Yeah.
And then with taxi drivers prefer shorter paths, maybe.
Let's try.
I always wonder that with Uber drivers, like whether they're, sometimes you go on a longer route, maybe they just want to cruise. Yeah. Okay. Back to this. So basically, the feature. So equation 2 is a distribution over trajectories. So zeta is a trajectory, and you can figure out what the probability of a specific trajectory is by using this equation. And like what this equation is like this is the reward or return of a trajectory. You take it to an exponential, you use it as a power, and then it's divided by some constant zeta, or I mean z, which is just like a normalizing factor. And what they point out here is like, if just thinking about it, it says plans with equivalent rewards have equal probabilities, and plans with higher rewards are exponentially more preferred, which makes sense because there's an exponential here.
So you actually normalizing the exponent probably would be sensible.
And then they talk about some convergence, like that this will converge. The normalizing factor will converge through learning. Yeah. And they talk about basically what formulations you need to use for that. Then this is all the math for a deterministic MDP. So an environment where when you take an action and you're a certain state, you'll go to another state. And there's no uncertainty. And then they extend it to a stochastic MDP, which I actually didn't think was, I mean, they don't use that in any of their experiments. So it was just kind of like a novel, I guess it was just because they can, kind of novel contribution, but it wasn't really useful to them. And so
There's a chat message.
oh, sorry, thanks. How do I integrate the circumference of the sun with an equation? I don't think that's relevant to this discussion. Anyway, So this discussion. And then let's see, the what? Is it, we'll just continue. So non-determinate. So they talk about stochastic MDPs. And the only difference between a non-stochastic MDP and a stochastic MDP is, well, they both have a state transition distribution, but for the non-stochastic version, there's only one outcome for each state action pair.
Which type of problems would be non-deterministic?
In the real world?
Yes, like I'm struggling to think of a open learning problem without nothing.
Okay, let's see.
Pretty well that there's wind, there's not statistic way, so you might move the
Yeah. Okay, but assuming that the wind is not part of your state.
Yeah, but that would be an example of that's a good example, which is when you have disturbances that you can't observe.
Okay.
And you're
And what's stochastic, the path or
the transition. So you say like, I'm in this state and I'll take this action. And then you don't actually get to the state that you wanted, you get to another state. So
that's probably possible. You can try to score a goal by going either left or right, but it might not work.
yeah. So like here, there's like this in C, this is a stochastic MDP. And what they're saying is that if you're in state 2 and you take action A4, then you could go to state 1, but you could also go to state 2. Yeah, and then they just show the math for this, where they say like this is the exact equation given a stochastic MDP, and we'll relax it by saying if we assume that transition randomness has a limited effect on behavior, which to me that means that so you don't know what the impact of your action would be, but it doesn't really like it won't really affect which action you choose to take.
I was quite confused. So this equation sums over the observed path.
Yeah,
So do this thing, a path that has no been observed gets zero probability effective.
pretty much. Again, that's the there's a reason why you don't use there's not a lot of inverse reinforcement learning in the real world. It's because like it's ill-posed. It's like a weak learning signal. It's a hard problem to get good policies, to get good results for. Yeah.
Imagine that this assumption is like, even if it's not stated in every paper reinforcement learning, it's usually assumed that that like this uncertainty is not going to affect your decision making. So I don't think I've ever seen not an inverse, but like a forward reinforcement learning problem where they say, oh well, but actually the probability of the state is different, whichever action I take, they usually just.
No, there's a lot of that kind of stuff. And you have like stochastic MDPs and you have partial observable MDPs. There's different ways of taking into account the stochasticity. Yeah, they usually don't assume a deterministic environment.
One question. So what is actually this MDP model?
Markov decision problem.
What exactly does it mean? Does it mean that the path is generated by going stepping forward, making a decision at each point? Or
Yeah.
Yeah, the MDP is just that so your next state only depends on your current state.
Probably
Which is reinforcement.
yeah, unrealistic assumption for the problem at hand.
Yeah. What's
That's why I think this method actually works well compared to the others, because it actually this prefactor has actually also this view. Oh yeah, this part optimizes whatever I need. And as I think you mentioned the tropic factors, there are 5 ways of getting to this point, which makes it more likely. This is probably not important in real life because no text alert. Oh, I could have done here by 5 different routes, so I should use it even more.
Yeah. But so, the solution that they usually have in reinforcement learning is say that you're making the assumption that just your state is enough to make a decision. Is you just extend your state to be the history of states.
Yeah.
So then your state is Markovian.
again, you typically know where you want to go, so that's probably not quite correct.
Mm.
The problem in small problems, ranging from a start location to the location, break it through every intersection, and then what kind of, so you just do a net policy product at each intersection,
Mm.
and then you would use that across the cost function across the possible routes. See what I'm saying?
Yeah, yeah.
Yeah, by learning it into making it hard.
Yeah, that's how the formulations for that are called, like usually they're under the framework of hierarchical RL. And there's a couple of different ones. Again, it's really hard because the whole idea of hierarchical RL is that you abstract in terms of time the problem. And so you have, like, you solve things, different problems at different time scales. But like, how do you know how many abstractions levels to go up? Usually that's something that's hand defined. And then, because usually for that problem, what you say is like, okay, every 10 time steps, I'll make a larger decision. And then within those 10 time steps, I'll plan according to my decision. And then you have to figure out how to define like the policy within that those 10 time steps so that they generalize to the problems, the abstract problem, like more abstracted problem. Anyway, so we've kind of gone over the math so here's the training objective that they're trying to maximize for imitation learning, inverse reinforcement learning, which is they want to maximize the log probability of the observed trajectories given like by choosing the optimal parameters for their method in their reward function. And they point out that it's really easy to calculate the gradient for this method, which is I think what this is basically saying is f tilde is the expected feature counts over the trajectories. So the what we were talking about before, and then this second right hand, or like this second term in the equation, what that is that it's basically the expected feature counts given the policy. So you're just trying to match them between the policy and the observed feature expectation features of feature counts. Yeah.
And it's interesting that you could have equally likely looked at all the feature counts on average and found separately the theta rate. If I know that on average the first feature has value X, I could find the theta. I think that
yeah, that's
then you have to, because of the linearity, right? There's no action. You just could find theta separately for each. That probably would well.
yeah. Is there any? I'm not sure. Yeah. So anyway, we talk about some stuff, and here's the algorithm. So I just wanted to go through it really quick because it took me a second to understand. So actually, what you do for this algorithm is you start in all what are called the terminal states of the environment, which are the states where you could end or finish, and then you backtrack from them. So you're saying that like this is kind of like the frequency of the terminal states is 1, and then you backtrack from them where you weight previous states based on like the reward and the transition function. So the likelihood of getting to if you look at this equation here, basically what it's saying is ZSK is the frequency of the state you are in at like time step, at your final time step, let's say, and then then you're multiplying it by the probability of being in state SI, given the action that you took and being in the final state SK. Or actually, no, I think I'm doing it the other way around. You're in state SI, and what is the probability that you were in state SK, given that you performed action IJ? And it's also weighted by the reward that you would get from Yeah.
Send the other way around, what's the probability of getting into K, given that you are in I, but you're going backwards?
Yeah, it looks like it's going forwards, but it's going backwards. That's what the only thing I should have said. Yeah, because I think.
Yeah.
So the probability of landing in K is going to depend on the state and the action. So which actions you take.
Yes, but because we
It's
don't,
gonna be him, isn't it?
because we don't make the action out of potential. And that's like, sort of, this is a trivial sort of
Do we?
piece of information.
Yeah, but you have one, so the set A, I, J depends on the actions for each action, you have one piece coefficient.
Yeah.
And then, yeah, so the state is fixed and each action is going to produce one set.
So
Which
we
is,
do have states that have more ways to get into higher.
You have you count states.
But some, because the more states go into, they do come with higher. Or because the sum of all.
Well, you're backtracking, so it would be, I guess, states that you could get most terminal states from. And then you calculate the probability. Basically, this is like calculating. Oh, could you guys mute the microphone? So you basically 3 is calculating the optimal policy given your current reward vector, and then you calculate using your optimal policy in the forward pass and summing frequencies your state visitation frequency. So for each state, what's the frequency that you visited? So I'm explaining it really poorly, but essentially what you do is you get your current reward function, and then you calculate what the optimal policy is given that current reward function, and then you update it. So it's kind of like expectation maximization. You calculate your optimal policy given your reward function, then you update it to make your observed trajectories more likely given your reward function. And so this is really cool math, but if you think about the fact that like that calculation is actually really intensive, because for example, the classic reinforcement learning problem, it's just trying to find the optimal policy. So for this problem, you have to do that over and over and over again. So it's actually like way more computationally intense than trying to find the optimal policy in the classic reinforcement learning problem. So that's another reason why it's not really done a lot. Cool. Well, we can go back if anyone has any questions. But so the experiment that they run this on is trying to figure out the driving preferences of taxi drivers in Pittsburgh, Pennsylvania. And they actually have a pretty large MDP because they go for like, the states are like 300,000 roads in the city, and there's like 900,000 actions in terms of transitioning between roads. And one of the main assumptions that they make is that we assume that reward weight is independent of the goal state, and therefore a single reward weight can be learned from many MDPs that differ only in goal state. Which basically what they're saying is that each taxi driver has a different goal place they want to go to, but the way they drive is independent of that. And we want to figure out how they choose how they're going to drive.
But so it's like normalizing by the length of the path. We're not a bad idea.
Yeah.
This context.
That's a really good point. Which I guess would be, instead of summing the feature counts, they would just take their, calculate the mean.
Of course, you have to know the whole path, right? Then maybe this back and forward, this is not great because you don't know at 2.5 how many more steps are maybe going to. But again, if you optimize it on this higher level, you might still get to the low. And then it's a lot more tractable.
Based on,
You don't have to count paths.
based on an MDP anymore. So you
But
map,
then
for
it's
example,
different.
then your next state depends on also on the future states. Because the length of the path. So
Which
yeah,
is maybe not a bad assumption, but it's the problem.
yeah, then you can't use reinforcement learning.
It's a shame.
You need to write a new
Yeah.
method.
But I actually also feel like these linear reward functions don't make a lot of sense in the case where your reward function is like goal dependent. Like, I don't think this math works for a linear, or not that the math works, that it's hard to make a linear function in terms of state that is goal dependent unless it's, and still translate to multiple MDPs. So anyway, another thing I think that's interesting is they have like, so they have 13,000 distinct trips as their data set, and they only use 20% in their training set, and they test on the remaining 80%, which usually you see the opposite. But I guess the whole idea is that you want to learn from a small number of expert trajectories. Yeah, maybe. Yeah.
So how does the testing work here? Like, you would train a reinforcement learning model with the reward function that you extracted from the first 20%.
So what you would do, how does testing work?
Yeah.
Okay. So for testing, what they do is so up here in the all these equations, you can calculate the likelihood of a trajectory. And so they have a number of things that they test. One of them is the likelihood of a trajectory, which is this number here. Another one is if the agent was in, like, they give a trajectory and they use the policy that's induced by that reward function to choose which action to take at each state. And if they match, the trajectory matches exactly the expert behavior, then that's what this is. So they're saying, like, in the I don't know, like 8,000 trajectories that they got for each method, like for their methods, 80% of them matched perfectly. And then, oh, why is this lower? I thought this was it. Let me see. They say it over here. We say the model's most likely path estimate with the actual demonstrated path and evaluate the amount of the distance route shared. Oh, okay. So that was wrong. This is that like the percentage of the distance that's shared. Do you get what I mean? Like, did they take this? How much of the route is the same? And then in the second one is like, how much of the data set, for how much of the test set did they match into more than 90%?
So how do they find actually the probability? So once you know your potential, you can find the most likely path if you take, right? Unless there's some process, right? Then is that how they do? They find the most likely path and then say 90% of the time. That does.
No, I think you said the model, the first one compares the model's most likely path estimate with the actual demonstrated path. Yeah.
They really should have done intersections rather than distance.
And they compare it to two models. And there's like one last thing I wanted to go over, which is they point out another model, which is this Bayesian IRL and hybrid IRL. And what they point out is in like the way that they show that their method is better is that they say that going from A to B, all paths have the same reward, but other methods would prefer going down path 3 and then getting to B versus going the other way and then taking path 2 or 1. And that's because there's a branch if you don't go down path 3. And so these other methods don't like branching as like if there's multiple ways to get, they prefer a method that has only one, has as few branches as possible, so as few likely ways to get to the destination as possible. Yeah. Yeah, and so the results, what they show is that they have with a statistically significant factor, their results are better, even though they're not that much larger than the other ones. They're enough that there's a statistical significance. And yeah, I forget. I think they just show that like riders, the taxi cabs prefer driving on highways versus local roads. Like the learned cost function goes up. Yeah.
It might be those highways go straight to.
Yeah. There's a little bit of that in this, in the sense that you wonder how much of the results that you got automatically could you have just figured out with some simple reasoning as a human being. But they do talk about some results that this is useful for. Like, I guess is it this method or is it? Yeah, I guess it's this method because you can do density estimation. They point out that like this enables a range of new applications, including warning drivers about unanticipated traffic problems on their route without ever explicitly having to query the user about route or destination, optimizing battery and fuel consumption in a hybrid vehicle, and activating temperature controls at home prior to that driver's arrival. So it's basically saying with this, because we have the cost function, we can figure out what route they're going to take, or we can figure out what destination they're going to, and then make suggestions accordingly. Is there anything else? There's one more page, but
It's of course also like bias in the way. If you sample from a region, because the features are not randomly spread across the maps, right? So if you sample only from cities where you have highways or so, it will on average show higher your data set no matter which box you take.
yeah.
And I think this would potentially, absorb
That's the data problem we were speaking about before. If a new city has a different distribution, you need a different agent anyway. Navigate the city. Or a different reward function.
Well, unless the preferences are, well, I guess, yeah, because you use them to figure out what policy to take. It's an interest. I like this problem because it points to a way to figure out how to figure out people's preferences, or like how things, complex systems behave. But like there's so much lack of structure in reinforcement learning problems that it's hard to learn useful things with them.
But he sort of shows that people don't care about branching, which makes sense.
Yeah.
So you think that even if you already train your reinforcement learning agent, you can use this method to either find a better reward function or to better understand why the agent is.
Well, if you've trained the reinforcement learning agent, you have the reward function, and so you don't need to recover it.
Yeah, but like, so would it be possible to find a better reward function? Using this method?
No, because unless you have expert trajectories that perform better than your reinforcement learning agent. This one is only useful if if you don't know. Yeah, because if you don't know why the person did what they did or why the agent did what they did.
The podcast that was talking about some of the game of landing a lunar module on the moon in uncertain gravity. And they came to the conclusion that this method worked well. And then people really had understanding. And they concluded that what was just people are not good at physics and understanding their reactions. They're actually doing the right things. And so we might be able to unpick the problem into two components.
Are you talking about that Atari game that's like lunar landing? Yeah. I've done some reinforcement learning work with the Atari games, and that one, it's really hard to get an algorithm to learn a good policy for it, actually. I mean, unless you have a lot of compute and a lot of time, but it's like one of the harder ones. It's surprising. Yeah. Cool. I'm gonna stop recording.
Do you want to look something?
Well, we're done, so okay, I'm gonna stop. But I'm gonna leave the chat open just so people can hear our conversation if they want.